China has just put a sodium-ion battery into a production vehicle that can retain 90% of its driving range even at temperatures as low as -40 degrees Celsius. Meanwhile, many lithium-powered electric vehicles begin to lose significant performance long before reaching those conditions, with some struggling even in ordinary winter weather. What's even more remarkable is that this battery contains absolutely no lithium, no cobalt, and no nickel. The very materials that Tesla and nearly every major EV manufacturer have spent years fighting to secure. According to its developers, this new battery can last up to 3 times longer than today's best lithium-based batteries. It has also passed one of the world's toughest battery safety tests without catching fire, exploding, or suffering catastrophic failure. But the cold weather performance isn't what should worry Tesla, Ford, Volkswagen, or any Western automaker. The real shock is hidden inside a single number from what has become the largest non-lithium battery agreement in history. And once you see that number, you may realize the entire electric vehicle race is about to change. But first, a quick note: I started this channel for one reason: to explain the biggest electric vehicle breakthroughs before they become mainstream headlines. If that sounds valuable to you, consider subscribing. My goal is to reach 1,000 subscribers by the end of June, and your support helps make videos like this possible. Now, let's talk about what happened on April 27th. On that day, CATL signed a 3-year agreement with Beijing Hyperstrong Technology to supply 60 gigawatt-hours of sodium-ion batteries. At first glance, it might sound like just another partnership announcement. It wasn't. This was a full-scale production contract complete with delivery schedules and manufacturing commitments. To understand how enormous this deal really is, you need some context. Throughout all of 2025, CATL supplied approximately 122 gigawatt-hours of energy storage batteries worldwide. That figure includes every battery chemistry and every storage product the company produced. Yet, this single sodium-ion contract alone accounts for nearly half of that entire annual output. Think about that for a moment. A technology that was barely entering commercial deployment only 1 year earlier has suddenly secured a production order equal to almost 50% of CATL's previous yearly energy storage volume. And this is exactly why Tesla should be paying attention. For years, the EV industry has been built around one assumption: lithium would remain the foundation of the electric future. Tesla's factories, supply chains, mining investments, and battery strategies all depend on that assumption. But sodium changes the equation. Sodium is abundant. It is inexpensive. It is available in enormous quantities across the globe. And unlike lithium, it is not concentrated in a handful of strategic regions that can create supply bottlenecks and price volatility. If CATL can successfully scale sodium-ion production to tens of gigawatt-hours per year, the economics of electric vehicles could shift dramatically. The question is no longer whether sodium batteries work. The question is whether the rest of the industry can adapt before China turns sodium-ion technology into the next major battery standard. Because if this 60 gigawatt-hour agreement is any indication, the transition may already be underway. The order is specifically for grid-scale energy storage. Massive utility-grade installations that capture power from wind farms and solar arrays, then feed it back to the grid when demand spikes. The cells contain 0 cobalt and 0 nickel, and they are dimensionally identical to CATL's existing lithium storage cells. The same enclosure, the same rack layout. A grid operator can swap from lithium to sodium without redesigning a single piece of hardware. This deal sits inside an even larger framework signed in November of 2025, 200 gigawatt-hours stretching through 2035. That is a decade-long commitment to a chemistry that most of the battery world had dismissed as a dead end. Now, not a single gigawatt-hour has actually shipped yet. Economics still has to be proven in the field. But the bet has been placed, and the sheer scale of it tells you that something fundamental has changed. The question is, what? And the answer starts with what lithium has been quietly getting away with for a very long time. In 2023, in New York City alone, lithium-ion batteries caused 268 fires, injured 150 people, and killed 18. Most of those incidents were linked to e-bike batteries overheating inside apartments. The underlying chemistry explains why. Lithium-ion cells use organic solvents to move their ions around, and those solvents are flammable. If a cell gets overcharged, punctured, or overheated, the electrolyte can ignite. The heat from one burning cell can then trigger neighboring cells in a chain reaction known as thermal runaway. Then there is the cold weather problem. The American Automobile Association tested 5 EVs at 20 degrees Fahrenheit with the cabin heater running and found an average range loss of 41%. The worst-performing vehicle lost nearly half of its usable range. At freezing temperatures, lithium ions move so sluggishly that they begin plating onto the anode surface as metallic lithium instead of slotting between the graphite layers. That plating can grow into sharp, crystalline spikes, called dendrites, which can pierce the separator and short-circuit the cell. And then there is the supply chain. 3 countries control roughly 90% of the world's mined lithium. China alone processes around 65% of all lithium into battery-grade material and manufactures approximately 75% of all lithium-ion cells on the planet. Between 2020 and late 2022, the price of lithium carbonate climbed from around $10,000 per ton to more than $80,000 per ton. Then, in 2023, it collapsed by more than 80%. If you are a battery manufacturer trying to plan a multi-billion-dollar factory investment, your most important input cost is behaving like a cryptocurrency during a market crash. We built the most important energy transition in history on top of a material that catches fire in apartments, struggles in winter, and trades like a meme stock. So why did it take 3 decades to find something better? Because sodium was never the backup plan. It was the original plan. Back in 1966, the Ford Motor Company built the first high-energy rechargeable battery, and it ran on sodium, not lithium. The sodium-sulfur design achieved 150 watt-hours per kilogram, which was remarkable for that era. But it had one major problem. It used molten sodium and molten sulfur as its electrodes. That meant the entire battery had to operate at roughly 300 degrees Celsius. Imagine keeping a pizza oven running inside your car at all times. Not exactly consumer-friendly. The breakthrough that tilted the entire field toward lithium came 6 years later, in 1972. A researcher named M. Stanley Whittingham discovered that lithium ions could move in and out of titanium disulfide cathodes at room temperature. For the first time, someone had built an alkali metal battery that worked without being kept inside what was essentially a furnace. From that moment forward, every major laboratory, every major investment, and nearly every major career in battery science followed lithium down the road. Then graphite sealed the deal. Graphite is cheap, stable, and its layered crystal structure contains gaps almost perfectly sized for lithium ions, which measure just 76 kilometers across. Sodium ions are about 102 picometers across, roughly 35% larger. When sodium tries to squeeze into those same graphite layers, it forces them apart, destabilizes the structure, and degrades the anode after only a limited number of charging cycles. The practical storage capacity of graphite for sodium is essentially 0. So, when Sony launched the first commercial lithium-ion battery in 1991, graphite became the industry standard anode, and sodium suddenly had no realistic path forward. Over the next 3 decades, roughly $1 trillion of investment and infrastructure followed lithium. I think the industry gets too much credit for choosing the best chemistry. What it really chose was the chemistry that happened to work with the cheapest and most practical anode material available at the time. That is a very different thing. And for nearly 30 years, nobody had enough reason to go looking for an alternative. But around the year 2000, a Canadian laboratory found one anyway. A research group led by Jeff Don at Dalhousie University discovered that a material called hard carbon could reversibly store sodium ions in a way that graphite never could. Hard carbon is the structural opposite of graphite. Where graphite is a tidy stack of perfectly parallel carbon sheets, hard carbon is organized chaos. It is made by taking organic precursors such as biomass, tree resin, or even simple glucose, and heating them to between 1,000 and 1,400 degrees Celsius in an oxygen-free environment. The temperature is so high and the process so rapid that the carbon atoms never have time to organize themselves into neat layers. Instead, they freeze in place inside a permanently disordered structure filled with nanopores, irregular gaps, and random layer spacing. And those disordered spaces turned out to be exactly what sodium ions needed. Yet the discovery sat in academic journals for more than 15 years. The battery industry was simply too committed to lithium to pay attention. It was not until 2016 that CATL, already the world's largest battery manufacturer, launched its first dedicated sodium-ion research program. They committed approximately $1.44 billion over the following decade. 300 researchers, 300,000 individual test cells built and evaluated. Hard carbon's porous structure naturally absorbs water vapor from the air. Even trace amounts of moisture can react with the electrolyte inside a finished cell, generating gas and reducing performance. CATL solved this by chemically replacing water-attracting groups on the carbon surface with hydrophobic compounds that effectively sealed the pores. They also developed angstrom scale control over pore dimensions, tuning them just wide enough for sodium ions to enter, while remaining tight enough to maximize charge storage. Then there was the current collector problem: lithium alloys with aluminum, which is why lithium batteries require expensive copper foil on the anode side. Sodium does not alloy with aluminum, so CATL replaced copper with aluminum foil, reducing current collector costs by roughly 70%. The battery that emerged from a decade of this work has performance figures that sound like they belong to a chemistry that does not exist yet. But it does exist. It passed safety certification. And it is entering production vehicles this summer. According to Wood Mackenzie, one of the most respected energy research firms in the world, the actual cost of sodium-ion cells in 2025 was approximately $59 per kilowatt-hour. The cost of LFP lithium cells, meanwhile, was about $52 per kilowatt-hour. That means sodium is currently more expensive per kilowatt-hour than the lithium chemistry it is supposedly replacing. Not cheaper, more expensive. The reason is surprisingly simple. Lithium carbonate prices crashed by more than 80% from their 2022 peak. When lithium becomes cheap, sodium's raw material advantage almost disappears. At that point, the higher manufacturing costs of a younger, less optimized production process begin to dominate the equation. The cost advantage only returns if lithium prices rise again, and since lithium carbonate rebounded toward $26,000 per ton in early 2026, that is not an unreasonable assumption. But right now, it is still an assumption. It is still a bet. Ironically, the fact that the most widely shared number about sodium batteries is wrong makes the real story far more interesting. Because if sodium is not dramatically cheaper, then cost alone cannot explain 60 gigawatt-hours of factory orders. Something else lit the fuse on sodium's comeback. And that something else is what makes this story much bigger than most people realize. The real shift is not about one chemistry replacing the other. It is about both chemistries working together, each doing what the other struggles to do. CATL is not positioning sodium as a direct lithium replacement. Instead, the company is developing a dual chemistry architecture called FreeVoy, combining sodium-ion cells and lithium-ion cells inside the same battery pack. Advanced software continuously decides which chemistry to draw power from based on temperature, driving conditions, charging state, and energy demand. Sodium handles cold starts and low-temperature operation, where lithium can lose a substantial portion of its performance. Lithium provides the high energy density needed for highway driving and long-distance travel. Neither chemistry is forced into a job it was never designed to do. That is a much smarter design philosophy than simply trying to make one battery chemistry solve every problem. And for grid storage, the case may be even stronger. CATL's sodium energy storage cells are rated for up to 15,000 cycles while maintaining 80% capacity retention, along with a round-trip efficiency of approximately 97%. Those are numbers utility operators pay very close attention to, because a battery that lasts longer is often more valuable than a battery that stores slightly more energy. And these systems are no longer theoretical. Sodium-based grid installations are already operating in China. The Datang Hubei project, a 50-megawatt installation using advanced sodium-ion batteries, has been feeding electricity into the grid since 2024. China's Southern Power Grid also commissioned a 200-megawatt lithium-sodium hybrid energy station in Yunnan, managing power flows across more than 30 renewable energy facilities. It became the world's first grid-forming sodium-based energy storage system. And CATL is not the only company making this bet. BYD, the world's second-largest battery manufacturer, launched its own mass-production sodium-ion line in Qinghai Province during 2025. The facility targets 30 gigawatt-hours of annual production capacity and batteries reaching approximately 160 watt-hours per kilogram. BYD's first sodium-powered production vehicle is expected to follow soon. Think about what all of this means for ordinary drivers. In northern Chinese provinces such as Heilongjiang and Inner Mongolia, winter temperatures routinely fall below -30 degrees Celsius. For years, EV owners in those regions have watched their driving range collapse every winter. In some cases, vehicles lost 40% or more of their practical range. Entire months where the vehicle simply could not perform the way buyers expected. Those drivers may finally get that range back, not because engineers squeezed another incremental improvement out of lithium, but because they paired lithium with a second chemistry that actually thrives in extreme cold. And there is one final piece of this story that almost nobody is talking about. It may be the most important part of all. According to the International Energy Agency, China currently controls more than 95% of all announced sodium-ion battery manufacturing capacity worldwide. 95%. Think about that. The technology that many people assumed would reduce dependence on China's lithium processing dominance is itself overwhelmingly concentrated inside China. And so far, Western efforts to build competing sodium-ion industries have struggled. Northvolt, the Swedish company that many hoped would become Europe's answer to CATL, successfully demonstrated a 160 watt-hour per kilogram sodium-ion cell in late 2023. Then the company went bankrupt. Natron Energy, one of America's highest-profile sodium-ion startups, planned a $1.4 billion manufacturing facility in North Carolina. That effort also collapsed. Two of the largest Western sodium-ion bets disappeared before reaching large-scale production. There are still survivors. Peak Energy activated the first grid-scale sodium installation in the United States. Tiamat is building a gigawatt-scale factory in France. Reliance Industries acquired Faradion, one of the earliest sodium-ion pioneers, and is expanding production capacity in India. But none of those companies are signing 60 gigawatt-hour contracts, not even close. Meanwhile, China dominates nearly every measurable category. More than 10,000 of the roughly 14,000 sodium-ion research publications worldwide originate there. CATL has a decade-long head start. BYD is rapidly expanding. The patents, the supply chains, the manufacturing capacity, the first commercial vehicles, and the first large-scale grid systems are increasingly concentrated in a single country. That creates a fascinating paradox. On paper, sodium-ion batteries should reduce dependency. Sodium is abundant. Hard carbon can be produced almost anywhere. Aluminum is widely available. Nothing about chemistry requires Chinese raw materials. Yet almost everything about the industry currently runs through Chinese factories. Sodium does not automatically eliminate dependency. It simply changes the material that dependency is built upon. And unless the rest of the world builds its own sodium manufacturing base soon, this breakthrough may not weaken China's position at all. It could strengthen it for another generation. This summer, the first mass-production sodium-ion EV rolls off Chang'an's assembly line. Within the next year, the first wave of these massive grid storage orders will begin shipping. And for the first time in decades, the battery industry may be entering a future where lithium is no longer the only chemistry that matters. Subscribe so you're here when the first large-scale real-world performance data finally arrives.